Hello there. This is your introduction to physics, and in this chapter we will talk about units and dimensions. Now, in physics or in science, we only talk about quantities that can be measured, and such quantities are called physical quantities. So, any quantity that can be measured is called a physical quantity. And it is only the physical quantities that we'll talk about in physics, or in general we can say science. So to give you an example of a non-physical quantity, you must have sometimes said that you hate something, right? But can you measure that hatred? You cannot, right? So hatred cannot be called a physical quantity. Now, the reason I'm stressing this is that in science or in physics, we deal with quantities that can be measured. But the question still remains as to how can we measure them, right? Let's think of a very fundamental thing, for example, length. So let's say I draw a line which is this long. Now, forget everything you know about scales and I tell you to measure this line. How can you do that? Well, one way is that you define your own standard. For example, you could say that this length, so this is any given length, you take this length, take it as reference and say that I'll call this length as 1 zeta, right? So I've just come up with a unit which is a zeta, and I've chosen a length, and I'll say that this particular length, I'll call it 1 zeta, right? Now, using this reference, I can see in terms of multiples as to how long this given length is, right? For example, let's say that if I move this length along this line and I find that this length is 5 times the reference length that I have chosen. So if that is the case, I could say that this length is 5 zetas, right? So what we essentially understand from this example is that to measure anything, we first need to set standards, right? And for in case of length, you already know the standard units are centimeters, meters, kilometers, or miles. So now you can understand that these lengths, we ourselves have chosen them as reference so as to be able to measure any given length, right? So when we say that something is 10 meters long, what this means is that that particular length is 10 times the reference that we have chosen to call as 1 meter, right? So this defines the idea of units, which means that to define units, we have set some standards. For example, let's also take the case of weight. You know that weight, or you'll see, to be more specific, mass is measured in kgs, right? Whenever you buy something at the store, you buy it by kgs, right? So how did we come up with the idea of 1 kg? Well, it's simple. We wanted to measure mass, so we took a defined amount of mass and started calling it 1 kg. So if something had 5 times the mass as compared to our standard, then that particular thing would said to have a mass of 5 kg. So now, there are some quantities, some physical quantities that are made, that these are the quantities which cannot be derived. Well, if you take a closer look, you would also see that these are the quantities which cannot really be defined with the help of any other thing. For example, let's talk about length. Now, we saw how we measured length. Can you think of defining length in terms of any other known quantity? You cannot, right? Similarly, mass or amount of quantity or current, these are quantities which cannot be derived from anything else, right? So we have 7 fundamental quantities and the units of which are also shown in this table, and you should remember them. These units are the standard units. Right. So another thing about these fundamental quantities is that these quantities are in a way very fundamental, by which I mean that we cannot exactly explain what these quantities are, but we know how to measure these quantities and how to use these quantities to create other physical quantities. For example, you can see that we have used 2 physical quantities, which is length and time, to derive a physical quantity which is speed, right? Whereas you think about it, and this is something you'll have to really think about, it's very difficult to perceive what length really is, right? Well, I'll leave that thought to you. So the essence here is that we have used 2 fundamental quantities to derive another physical quantity, and this quantity, since it is derived from other basic quantities, is not a fundamental quantity, right? So now all the fundamental physical quantities we have, all 7 of them, they are given special symbols. For example, to write a few, mass is given the symbol m, length is given the symbol L, and time is given the symbol T. The entire list is shown right in front of you. So once again, you should try to remember these quantities, and you would see as we move forward, as we encounter more and more physical quantities, we'll keep discussing their dimensions, and it'll start becoming clear to you why we need to understand their dimension. Right. So let's talk about a few quantities and see what their dimensions are. Now, for the fundamental quantities, we have already fixed the dimensions, like the mass is m, length is L, time is t. Let's think about speed. So if you want to talk about speed, so speed is distance divided by time. So distance is length and time is t. So the dimension for speed becomes, let me put 3 arrows just to signify that equivalence of dimension. So its dimensions will be L, T minus 1. So this is the dimension of speed. So we usually use these. Let me first finish deriving the dimension of acceleration. Now, let's for now just take it as a fact that this change in velocity will have the same dimension as velocity. So if that is the case, the numerator has the dimension of Lt minus 1 divided by time has the dimension t. So let's keep them in square brackets. So we find that the dimension for acceleration would be Lt minus 2. Right. So this is the dimension for acceleration. Right. Now coming to the point of addition and subtraction, think about it. If I tell you that I add 5 meters to 3 seconds, does it make any sense? You cannot add length to time, right? Because it does not have any physical interpretation or any meaning, right? So if you add and or subtract 2 quantities, it makes sense if and only if the 2 quantities have the same physical dimension, right? So to give you an example, let me write an equation. So let's say x plus y is equal to a into b. So this is any general equation, but just by looking at this equation, what I can certainly say is that x must have the same dimension as y, right? Because then and only then I can add x to y. Also, if on adding x and y I am getting a quantity which is a into b, then a into b, the whole product, must have the same dimensions as x, which has the same dimensions as y. To see this in an example, remember the first equation of motion is V is equal to U plus A into T. Now, in this equation, you are multiplying, you're adding rather U to this term which is A into T. Now, we just said that such an addition is meaningful if and only if both of them have the same dimension. So, let's check for it. The speed you know is measured in meter per second or kilometer per hour. Acceleration is measured in meter per second square. So this A into T is meter per second square into second, making it meter per second, right? So you can see the unit becomes the same, right? Also, you can check the same thing dimensionally. Acceleration is LT minus 2. If I multiply acceleration with time, what I basically get is LT minus 1, which is the dimension of speed. And that is why this equation is meaningful and consistent, because the two terms which are being added have the same dimension. If they did not have the same dimension, there was no meaning in adding those two quantities, right? So, comparing these two equations, I hope the logic has become clear to you that whenever I see an equation like this, I can directly claim that X must have the same dimension as Y, and both of them individually have the same dimension as that of this product of A and B. So let's now take an example to understand this further. Let's take the example of work. Now work, you know, is force into distance. Now in case you don't know this, don't worry, we'll study this when we get to the chapter of work. Right now we're discussing this just to understand dimensions and units, right? So work done is defined as force applied into distance. Now let's look at the units of work as well as the dimensions of work. So if you talk about units, then force, you can derive that also. Force, you know, from the second law of motion is mass into acceleration, right? Now the unit for mass is kg, and the unit for acceleration, we just talked about it, is meter per second square, right? So the units for force become kg meter per second square, right? And the units for distance, you already know, is meters, right? So if we talk about units of work, it becomes kg meter per second square into meters. So the unit of work becomes kg meter square per second square, right? Similarly, if we were to talk about its dimensions, then its dimensions would be the dimension of force. Let's find out from this expression. The dimension for mass is m. That of acceleration we had seen is LT minus 2, since it's distance per unit, which is speed, further divided by time, which makes it distance per second square, or rather meter per second square, right? So this is the unit dimension for force, making it mLT minus 2. So the dimension for force is mLT minus 2. The dimensions for distance are obviously L. So you get the expression that it is mL square T minus 2, right? So this is how we can derive the dimensions of any physical quantity. Now we could discuss a lot of physical quantities, as you would certainly find in your books, but rather than going into quantities that you don't know about yet, we will keep discussing them as and when we encounter them. For now, we understand that units are defined for a way to measure these quantities, and these dimensions are defined because they help us identify that for any physical quantities, what are the fundamental quantities that are used to build that quantity. For example, when we derive this dimension for work, we can see that work is a derived physical quantity and it is derived from mass, length and time. Right. So for now, I'll not stress this any further. Rather, we'll keep discussing them as and when we encounter more physical quantities. Right. So now let's move on to error analysis. Now once again, this is something that we will discuss in more details when we go to experimental physics. The reason is this requires a better understanding of mathematics, which you will get during this course. So once you get that knowledge, it makes a lot more sense for us to discuss it then, but I'll give you a brief overview. So while discussing this, I'm assuming that you have very basic knowledge of calculus, right? So let's say that you have a quantity, let's say distance, which is equal to speed into time, right? So you're trying to measure the distance covered as product of the speed and time. Now say you know that there is some error in measurement of speed and there is some error in measurement of time. So how do you estimate the error in measurement of distance? Now to do that, what we'll basically do is differentiate this quantity on both sides. So if we do that, you can see we'll be able to write that ds is equal to v dt plus dv into t, right? I'm using the product rule, right? Now in the next step, you divide these two equations, so you basically get that ds by s is equal to v dt plus dv into t upon v into t, right? So now we can rearrange it into an expression that you will see in your books, which is ds by s is equal to dt by t plus dv by v, right? So to generalize this expression, what I can say is, if there is any quantity x which is a product of y and z, then the error in measurement of x is such that delta x by x is equal to delta y by y plus delta z by z, right? Or you can, if you strictly want to talk about the error, then delta x is equal to delta y by y plus delta z by z into the quantity x itself, right? And this quantity delta y by y or delta z by z can be called the fractional errors. So delta y by y is the fractional error in y and delta z by z is fractional error in z, right? So similarly, if you had a case where, say, on the other hand, if you had a case like v is equal to s divided by t, if this was the case, then once again on differentiation you'd get something like dv is equal to tds minus s dt upon t square, right? So once again, if you divide these two quantities, you get something like dv by v is equal to ds tds minus s dt upon s into t, so which can be written as, this will become, the t cancels out, so ds by s minus dt by t. Now at this point, there is an important thing to note. Even though this expression tells us to subtract these two errors, we know that if there is an error, it will only add to other errors, right? So the result that you will get will not be a difference but rather a addition, right? So always remember this, that in case of errors, once you get an expression like this, you never subtract errors, right? They'll always get added. So any fractional error is sum of all the fractional errors for all the quantities that are there. So to make a more general expression, let's say if we had a quantity, let's say y, which was equal to a raised to m into b raised to n divided by c raised to n, then, and I want you to derive this by yourself, you would see that when you differentiate this dy by y, so I'm writing the expression which is after differentiation and dividing, you can see that when you differentiate a raised to m, you'll have an expression of the form m into a raised to power m minus 1, right? And this a raised to power m minus 1 will later get divided by a raised to m, once again leaving with u with 1 by a, right? So check this yourself, you'll get an expression of the form m into dA by a plus n into dB by b. Now, by differentiation, what you'll get is minus of, so let's take another term, let's call this O. So it will be O into dC by C, right? But you know that errors are not to be subtracted but to be added. So this is the general expression for error analysis, that fractional error will be equal to the index of power into the fractional error of that quantity, right? So this expression you need not remember if you remember the logic behind this, but this is the expression that is used to find out or rather do the error analysis for any physical quantity.